In this video, we're going to introduce the concept of product integrals and product integration. In this video, we're only going to discuss the algebraic perspective, and we'll leave the geometric understanding until another time. So before we go into the discussion of product integration, let us first recall the idea of, the classic integration problem. So recall that the integral from a to b of f of x dx is defined to be equal to the limit as the size of the partition, or each subpartition approaches 0, of the summation from k is equal to 0 to infinity of f of xk, where xk is a tag in each of those subpartitions, times the length of each of those subpartitions, where delta x is defined to be equal to b minus a divided by n, where n is arbitrarily large in this case. So if that is the case, then we're going to define product integrations in a very similar manner. So we're going to define the integral, and I'm going to write an x here to sort of distinguish between an integral and a product integral. So the product integral from a to b of f of x raised to the dx power, and that's going to sort of, signal a product integral. This is going to be defined in a very similar manner. So this is going to be defined to be the limit as the subpartition size approaches 0 of the infinite product from k is equal to 0 to infinity of f of xk, where xk is a tag in each of the partitions, raised to the delta x power. Alright, so if that is the definition, the first natural question would be, well, is there a connection between product integrals and sum integrals? And that's going to be the first thing that I'm going to sort of go through, and then we'll illustrate it with a couple examples. So question, is there a connection between the integral from a to b and the product integral from a to b? Alright, so let us prove that connection. So proof. So we're going to start off with the product integral definition. So the product integral from a to b of f of x to the dx is defined to be equal to the limit as delta x approaches 0 of the infinite product from k is equal to 0 to infinity of f of xk to the delta x. So the first thing I'm going to do is use exponentials and logs to rewrite this expression. So we can rewrite this as e to the natural log of the limit as delta x approaches 0 of the infinite product from k is equal to 0 to infinity of f of xk raised to the delta x. So by the property of limits, we can withdraw this limit outside of this natural log. So we can rewrite this as e to the limit as delta x approaches 0 of the natural log of the infinite product from k is equal to 0 to infinity of f of xk to the delta x. So the natural log of the product is the sum of the logs, so we can rewrite this natural log and product, interchange them, and switch the product to an infinite sum. So we have e to the limit as delta x goes to 0 of the infinite sum from k is equal to 0 to infinity of the natural log of f of xk raised to the delta x. Now, by the properties of logarithms, we can take this delta x value down in front of the natural log because it is a finite number until we take this limit down. So we can bring that down, or we can bring it down in front of the natural log as well if we want to. So we can get that this is equal to e to the limit as delta x goes to 0 of the summation from k is equal to 0 to infinity of the natural log of f of xk times delta x. And what is this the definition of? Well, this precisely is the definition of a Riemann sum, or a Riemann integral. So therefore, this expression is the same as e to the integral from a to b of the natural log of f of x with respect to x. And here dx is multiplied by the sum and not raised to the power. So therefore we have this connection. Therefore the product integral from a to b of f of x to the dx is equal to the standard integral from ab of the natural log of x, or the natural log of f of x dx, and this integral is exponentiated. So sometimes you'll see this written as e equals to exp of the standard integral. And that is the connection between product and sum integrals. So let's work through a couple examples to sort of illustrate this. So if you're really good at standard integration, then product integration in this form is actually very straightforward. Alright, so first example. So let us find the product integral from 0 to 1 of e to the x squared to the dx. So by this connection, we've already proven that this is the same as e to the standard integral from 0 to 1 of the natural log of e to the x squared with respect to x. So in this case, the natural log and exponential will cancel out, so we're just going to be left with e to the standard integral from 0 to 1 of x squared dx. So the antiderivative of x squared is going to be equal to 1/3 x cubed. And then we're going to evaluate this as x goes to 1 and then x goes to 0. So as x goes to 1, this is going to be equal to e to the 1/3. And then as x goes to 0, that's just going to go to 0. So therefore what? So therefore, the product integral from 0 to 1 of e to the x squared to the dx is just going to be equal to the cube root of e. So that is the first problem that we can solve. Alright, so another example, example 2. Suppose we want to find the product integral from 0 to 1 of x to the dx. Now definitely if you have an exponential underneath, product integrals tend to be straightforward. So let's see how this turns out. So using our connection between product and standard integrals, this is going to be equal to e to the standard integral from 0 to 1 of the natural log of x with respect to x. So as we should already know, the antiderivative of the natural log is going to be equal to x times the natural log of x minus x. And then we're going to evaluate this as x goes to 1 and as x goes to 0. But before we evaluate the limits, I just want to break this down into its exponential components. So we can rewrite this as e to the natural log of x to the x, and then times e to the minus x. Because as you pretty much see, this is going to be equal to, so we can bring this x up here. So it's going to be x to the x, and then that e to the minus x is going to go downstairs. And of course, this is going to be evaluated as x goes to 1 and then as x goes to 0. And since we have 0 in the logarithm, this is going to be a limit as x approaches 0 from the right. Alright, so of course e to the natural log is going to cancel, so this is going to be the same as x to the x times e to the minus x, evaluated as x goes to 1 and as x goes to 0 from the right. So as x goes to 1, what do we have? Well, that's going to be 1 to the first times e to the minus 1. Subtract the limit as x goes to 0 from the right of x to the x times e to the minus x. So as we already should know, as x gets close to 0 from the right of x to the x, that's going to be approaching 1. E to the minus x is going to be approaching 1, so that's going to go to 1 as well. So we have this is going to be e to the minus 1 minus 1. So we can rewrite this as 1 divided by e minus e over e, which is going to be our 1 minus e over e limit. So therefore we have that the product integral from 0 to 1 of x raised to the dx is going to be equal to 1 minus e divided by e. And that's another example of how to evaluate product integrals. So pretty much evaluating product integrals is just a matter of transforming it into a standard integral and working it in that form. And the connection between these two is that the product integral from a to b of f of x to the dx is equal to e raised to the integral of a to the b of the natural log of x, or the natural log of f of x, with respect to x. This is the main connection between the two. Now there are some other alternative definitions of the product integral, but one can show that these definitions are connected, not necessarily equal, but they are connected. But we'll discuss some other alternative definitions in upcoming videos.